It's human nature to believe that if you've been doing something all of your life that works for you, that there isn't really a need to change. And the old adage of saying, if it ain't broke, don't fix it, kind of applies here. But the problem with that is things don't have to be broken to be inefficient, right? The idea of saying that I could go and chop down a tree and then I could dull my axe and that it would take too long for us to go back and sharpen the axe, so I'll just keep beating on the tree harder and faster, is some of the history of humankind that's fallen into this trap repeatedly. And the number one example I like to bring up for this one is if you talk about how you measure temperature, or in fact, most of the ways that we measure things in the United States. Now, temperature specifically, we measure in degrees Fahrenheit in the US, and this makes sense to us because we grew up understanding it. The problem is that on its own, temperature measured in Fahrenheit makes very little sense to anyone else, which is why most of the rest of the world uses Celsius. So to understand this, let's actually take a real quick history trip. Fahrenheit was one of the first means of measuring temperature invented by someone who is named after, and it was invented as a scale where originally 0 was set as ice and 100 was set at the human body temperature. Now, obviously today we know that 98.6 is a better average, but you can see that that's just about at 100, where somebody who was making thermometers for one of the first times would have called that 100 degrees, and we would have kind of adjusted it as we went on. Now, the reason why we don't still have the bottom of that number scale, the 0 mark at ice, is because since then we've been able to recognize things that were colder. And the inventor, not being a fan of negative numbers, every time he recognized something that was colder, actually would shift the scale up. So that's why it was originally 0 for ice, but when we found out that ice water mixed with salt was even cooler, then that shifted up so that was the new 0. And then eventually we could get even colder days than that were, experienced. And so that became the new 0. And what we eventually got left with was what we have today in our Fahrenheit scale. Now, all of this was scrapped during the scientific revolution. So the Celsius scale was invented based on water. They decided that at 100 degrees, they were going to say that this is when water boils, and at 0 degrees, this is going to be when water freezes. And this was almost universally accepted as a much better means of measuring temperature. After all, I could calibrate things very easily by just going out and getting some water and either boiling it or freezing it. So let's use this idea of temperature and converting for the rest of the world as the basis for today's lecture. What I want to talk about in today's lecture is one-to-one functions and this idea of inverse functions. This is some vocabulary we will learn as we go along. But what I want to start with is just a simple question. So here we have the method for converting between Celsius, which again has logical assumptions like water freezes when it's 0 degrees. This would make sense. At the bottom of our temperature scale, water is going to freeze. Good. And it's going to boil when we get to the top. Again, this makes sense. Compared to Fahrenheit, which was invented under super secretive conditions by an instrument maker afraid of negatives and fractions. Now, if we want to be able to communicate with the rest of the world, it would be helpful for us to be able to take the way that they measure temperature and convert it into a way that we measure temperature. We'll call this a form of empathy, if you will, where we will be able to have this common language of mathematics or functions that are going to allow us to switch from our language of Fahrenheit into somebody else's language of Celsius. So here are the method that's required to convert from Celsius to Fahrenheit. First, take your temperature that's measured in Celsius. So this would be something that is measured by another country, and we're going to multiply it by 9/5. Interesting. Okay, we're going to take that, we're going to multiply it by 9/5, then we're going to add 32 to the result, and we're going to label this thing F. And F is going to be the measurement that we are going to call the degrees in Fahrenheit. Now there's a lot going on in here, so it might be a natural inclination at this point in the semester for us to say, instead of looking at this as a 1, 2, 3 step, let's just write a function that captures all of this. So the first thing that happens is we are going to take a temperature C, and it says we're going to multiply this by 9/5. So maybe we'll say we'll multiply it here by 9/5. And then it says we're going to add 32 to it. No problem. And we're going to call this entire thing F. And so now we've got this function, this method of switching between our degrees Celsius to our degrees Fahrenheit. And if we even wanted to write it as a function a little bit more explicitly, we could say that this is a function that I'm going to call F, my Fahrenheit function, that is based on an input or a question of degrees Celsius. So somebody is saying, okay, what does, I don't know, 22 degrees Celsius mean in Fahrenheit? And we would say, okay, well, let's take your number, let's multiply it by 9/5, and then we'll add 32 to it. And this is actually going to be the method for us switching between your way of measuring temperature and my way of measuring temperature. Now, this is one way of doing it, but I'm a little bit curious, what would be the way of doing this in reverse? What would be the function C as it had depended on the question of F? Now, in mathematics, we'll often call this an inverse, because in inverse, just like in the word, if you talk about an inversion or a table or inverting something, is this idea of flipping around the question and answer situation. So we're trying to figure out what would be the way that we would go backwards on this. And that one's a really interesting question. Let's first start with going and looking at the pictures, the graphs, to maybe have a better understanding of why these functions are about to play with each other the way that we are thinking. So let's start off with first, what are we talking about? We have a function f that we just figured out. And here I will have to say that it's depending on x, because it's going to assume that x is my input question. And then we'll put it in 9/5 times x plus 32. Okay, so it went off the paper. Let's see if we can go find it. There it is. It just moved a little bit higher. And this would make sense. It has a y-intercept of, it looks like, about 32. And then we can see that it's actually going to come down here to say that when I have somewhere around, I don't know, negative 18-ish degrees in Celsius, that would be what would be considered 0 for Fahrenheit. So we can pull out some interesting little tidbits here. But the thing I want to talk about is what would happen if I wanted to invert this. So let's go ahead and say invert. We'll say invert the function. And we'll say invert f. And so this red graph that it has created is what the computer thinks is the inversion. Now, it might be interesting to figure out where these things come from. Why did it choose to do this in such a way? After all, if we look at the equation it came up with, it looks quite similar to what we had originally. It's just that it has the 32 and some subtraction. It has the 9/5 and some division. It's put it on the denominator. So what's happening here? Maybe before we get into the algebra of it, let's just see if we can find some interesting points. Like, let's find this point up here. What is this point? Let's grab it, find out what the value is. We'll give it a label and a value. There we go, 0, 32. Okay, so that means that we went over 0 in order to go up to 32. Interesting. What's this point down here? Let's give it a value. This one is 32 and 0. Now this is kind of interesting. Let's notice what happens. We're getting this idea of flipping. In the first one, I had 0 as my question. The question was, what does 0 degrees in Celsius mean? And the answer comes out, it says 32 degrees. So when the rest of the world thinks 0 degrees Celsius is when water freezes, the US thinks it's when we hit 32 degrees outside. But if we flip that, then on this red graph, what it's now saying is when the US thinks that it's 32 degrees outside, it's when water freezes. The rest of the world thinks it's 0 degrees. Same information, we're just changing the order of the conversation. Over here and figure out how is it that we might switch this question and this answer. Well, as we might have figured, if we wanted to solve out for Celsius, perhaps I wanted to have something about this Celsius over here, then I would eventually need to have Celsius alone. Just like when I had Fahrenheit alone, I was able to determine something about Fahrenheit. So let's think about all the ways that we could do that. To keep what's keeping Celsius from being alone right now is being multiplied by 9/5, and there's a 32 being added on. So perhaps we'll start off by saying that I am going to take my equation, f is equal to c times 9/5 plus 32, and I will try to get c alone by first subtracting 32 from both sides. That'll give me f minus 32 is equal to c times 9/5. And if we wanted to get c still alone, we would divide by 9/5 on both sides, and that should be enough to get us a good answer. That our Celsius function would be taking any input of Fahrenheit, subtracting 32, and dividing it by 9/5. And to tie this back into what we were just seeing on the computer, in Geogebra land and the online computer graphing software, since we had to use x's and y's, it was looking at this as saying f of x equals 9/5 x plus 32. But over here, it was viewing this thing as c of x equals x minus 32 over 9/5. Okay, so some interesting things to note here. How is it that we invert a function? Well, we do the same thing that we would normally want to do whenever we flip something. We just think of the idea and then do it in reverse, and then we just handle the consequences as it may be. But the interesting thing to note is that just like in this GeoGebra over here, the idea of what is x is just an idea. X here does not mean Fahrenheit, it doesn't mean Celsius unless we want it to mean. All the computer system knows is that x is a question that I am asking, and that the f of x, or in this situation, this c of x, we could call it, is just the answer that we are getting out. So we're going to be playing around with these ideas in this class, but if you had any questions on this, make sure you pause the video and ask. Otherwise, take a moment and fill out the rest of that worksheet so that you can put some observations, your conclusions, and justifications for why everything we just did up here makes sense. Okay, so let's jump on in. We want to try to relate these new ideas back to something that already makes sense to us so that we can, not have to be learning something from nothing, that instead we can just kind of extend our model of logic to include this new idea. So I'd like us to start off with just doing a quick little recall. So first, if I said what is the opposite of addition, or if I said what the inverse of addition is, this is a place where we've used inverse before in a mathematical context. And most of you would know exactly what the answer would be. So the inverse of addition would be whatever I use to undo addition, which is subtraction. So we can put that in. So we'll say subtraction is the inverse of addition. And if I said what's the opposite or the inverse of multiplication, most of you would be comfortable saying that that is division. After all, addition is nothing more than putting additional things into a pile, growing a value. Subtraction is nothing more than taking away that growth or undoing that growth. Multiplication is repeated groupings or repeated addition. And division is nothing more than taking out chunks in the same idea. So we get this idea of inverses, flipping it around. What's the inverse of a square root of something? Well, if I originally proposed that a square root was nothing more than saying I have a square, and perhaps my square is 4 big, and I wanted to say, okay, where did that come from? And it came from a side length of 2, then flipping around this entire thing would say, okay, well now, if I, instead of having a side length of 2, I would like to know how big my square is. I'm just saying the exact same story in reverse. So instead of going from a square to a square root, we could go from the square root to a square. So that would be the inverse of square rooting. It'd be a square. And what's the inverse of squaring something? Well, that would be, this one we have to be a little bit careful on. You might want to think it's a square root, but as we've seen in problems before, the inverse of a square is actually a plus or minus square root. And so this is going to be our first insight into what happened. Let's again go back and see what the difference is. If I said the inverse of square rooting something, so square rooting says I have 4 and I got to the 2, I'm already here. That's what I know, is that my square root is I can say what's the positive starting place of a square, and that's what gets me to 2. That's what it means to square root something, is to find the positive starting place, starting side length of this shape. And then if I said, okay, I want to go backwards, the only square I can make out of the number 2 is 4. So that one works out just fine. But if instead I said that I took a number and I used it to make a square of 4, how big is that number? And I go backwards in that logic. This number could have been 2 or negative 2. So we have to be a little bit careful in this idea of doing and undoing. Order matters. So this is our first insight. This is going to come back up later. Okay, so here's the question. What is the opposite or the inverse of something like this? This should be able to have an opposite. After all it says is take a question X, do a bunch of stuff to it, and get an answer. So the opposite of that would be, here's an answer, do a bunch of stuff, get me back to the question. Okay, so our question is, do I have an opposite of this? And if we do have an opposite of it, is it to a function? Okay, so let's play around with it. What does it mean to be the opposite of a function? It means that instead of going from a question to the answer, I'm going from the answer to a question. Okay, very nice. So that means that if I was originally going from some kind of x value to an f of x value, or something that we will normally refer to as a y value, that now I can look at this as saying that I'm going from a y value, or an f of x value, back to my question of x. Now, obviously, this is going to be a little bit weird, because if you asked a question into the opposite function, it would think it was just a question, but it might be an answer, but an answer could be a question. We're going to have to keep track of the storyline here. This is where the story really comes to play. But the idea of an inverse just simply means that I am undoing what I normally would have done in my original function. That's a nice one to latch onto. So over here we have that this is my function. Maybe we'll call it f. This over here is going to be f inverse. Okay. So what is the opposite of this function? Let's think through this one. What are some things that are happening? Well, I'm starting off with a question of x, and I'm putting it in on the numerator and on the denominator in a strategic way, and that's getting me some kind of answer. Maybe I'll call the answer y, because I'm about to be playing around with this. Okay, so my first setup, I have a question, it's getting me to an answer. In my inverse, I would be asking the answer and getting a question. So let's play around with that. What would that look like? I would be asking the answer, so maybe I'll put y's in there instead, and I'd be getting the question. Take a moment and pause if this feels a little bit weird, but the idea being that if all I'm doing in functions is taking questions to answers, then the opposite of that would be taking answers into questions. Now this feels a little bit weird, because obviously we would want to know what the result is at the end of the story, just like we wouldn't just want to say that I could go backwards. We would want to know what going backwards looks like. So let's see what we can do to kind of map all of this out. So the first thing I'm thinking is that we could try to get this so that there's only one y, even though there's a bunch of y's over there right now. And so we're just playing. No necessarily right way to do this, just a way that might work. And what's annoying me is I don't like that I have a numerator or a y on the numerator and the denominator. So maybe I'm going to multiply both sides by 2y plus 3. And so that would get it on the right-hand side and cancel it away from the left. Okay. Then I have y equals 2 times xy plus 3x as a way of getting rid of those parentheses. And then I could get all my y's on one side, so I get y minus 2xy by subtracting the 2xy from both sides. That would cancel it out on the right and get it to the left. Oh, and then look at this. The problem might be that I have 2 y's, and 2 y's is annoying, so I could factor it out, so I only have 1 y. I have y times 1 minus 2x equals 3x. And then from here we could say, okay, y equals 3x over 1 minus 2x. Oh, there we have it. Okay, so I've kind of got two different things that I played with. On the left-hand side, I started with saying I have a question and it gets me an answer y. On the other side, I said I started with a y, it gets me a question x, which I could also write like this. Now this part becomes a little bit confusing because I have y appearing in two different places. Over here, it's like I have y is equal to x over 2x plus 3, but over here I have y is equal to something different. So here, let's take a moment and give it better labels. This is where our function notation will help us organize our thoughts a lot better. And so instead of calling everything y, let's call this over here x is equal to, or x over 2x plus 3 is equal to f of x, our original function, and we'll give this a nice little box. And on the other side, we'll call this f inverse, something that I will explain in a moment why we normally write like this. Okay, f with a little -1 in the top right. So this is what we mean by when we write all this symbology for right now. I'm just going to let you know that's what we call or how we label our f inverse. Okay, but let's write down a definition of f inverse. So I'm going to actually leave this one for you. Think about what f inverse is. We created this thing through a story. We started off by saying I have an original function f that takes me from a question to an answer. And then we flipped it and we said, well, what if instead of asking the questions, I was asking answers and I wanted to get at the question. That gave us our second structure. So we went from here as our first relationship to here saying I should be able to switch the order, and then down to here, which now gave us a label to say, look, I have switched the order and I got something, okay? So Here we have it. What is the opposite or the inverse of this function? It would be this one down here. And so I'm going to let you write down exactly what inverse is, but keep in mind that there's two things, inverse and function. First thing, inverse. It has flipped something. So let's go ahead and write down inverse, and you're going to put a definition right here. Inverse, and explain what inverse is. And then we have function. And I'll help remind us about this one. Function is anything that takes one question to, at most, one answer. So now it becomes a very natural question to say, can we do this with everything? Is it always true that if I switch my X and my Y, if I switch my attention from one input to another area's input, that I might be able to do this with any function? Does every function have an opposite? Well, let's take a look here. So let's say consider the function f of x equals x squared plus 3. Let's determine its inverse. We'll do this both do it graphically and algebraically. So graphically is probably the easiest one first. Let's recognize a couple of these points. This one here is going to be 0, 3. And we could also figure out by plugging in 1 that there's a point right here at 1, 4. Similarly, there's another one over here at negative 1, 4. Okay, so we've got all of this. If I wanted to graph the inverse, I just have to flip which one is the question and which one is the answer. So let's go ahead and do that. I've got 0, 3, and instead I would want to plot it into 3, 0. So that'd be one of the first ones I would want to flip it. And that would be, let's see, 1, 2, 3, 0 would be right here. So I'll put it down right there, 3, 0. Let's draw it over here. It's going to get in the way in a moment if we don't. All right, 3, 0. What about the next one? The next one would be from 1, 4 would change into 4, 1. So let's put that over here. 1, 2, 3, 4, 1 would be right here. This would be 4, 1. And then we would also have, let's see, 4, negative 1, which would go right here. And if we connect them all, we get an idea of exactly where this inverse appears. It appears right here. Good. Okay. How would we have done it algebraically? No problem. We would have started off with the structure of saying I originally had outputs that came from putting an input as my x, squaring it and adding 3. And so we would then say, okay, but instead I'm going to flip the discussion. I'm going to say that now I want my outputs to be the original question, the original input. And we'll do some reorganization to make this look a little bit nicer. So we'll say this could be then x minus 3 if you subtract 3 from both sides. And I could undo that square by not square rooting, plus or minus square rooting. Okay, so it's going to be a plus or minus square root of x minus 3 equals to y, which we might be able to label as an inverse function. But the thing I want us to check about, and I didn't mention this last time, so we're going to have to be careful, and we'll go back to see that it worked last time, but only because we got lucky, is the question, is this a function, this thing that we have just created? Can I label it with that f and the little negative sign on it? Well, it's all the blue stuff that I'm dealing with down here, and if we remember, a function is any time where if I ask a question, I get at most one answer. So let's go through and just check the points that we did here. If I ask the question of 3, what is my answer? My answer is 0. That works out just fine. There's not another time where if I ask a question of 3, I will get anything else than an answer of 0. Excellent. What about the next one? I'll say I'm asking a question of 4. Does the question of 4 get me more than one answer? And turns out, yes, it does. It gets me an answer of negative 1 and 1. So here we've hit a little bit of a conflict. Is this a function? No, it is not. Because it doesn't, let's see, because x has more than one y sometimes. That would be an okay, that's kind of an iffy thing of saying that it's a function. Let's see, can we phrase that any better? No, It's not because... Oh, let's use the definition. No, it's not because I don't always get one output for each input. That's much better. Okay, great. So is it a function? No, it was an inverse. It was not a function. So this is going to be the number one tricky part of this section is if we're going to call something an inverse function, two things happening there. It is an inverse. It also has to be a function. Now this, we should have been able to predict this actually now that we reflect back on it, because notice here, I had a plus or minus square root of x minus 3. Plus or minus, that's a choice. And that's why we ended up getting a plus 1 and a minus 1 when I plugged in 4. So we can be a little bit cautious and find out if things are going to be functions as we're working through the problem. We should get a structure that gives us one and only one output if I want to be able to call it not only an inverse, but an inverse function. Okay, good. So let's check our solution against what the computer software does. So let's go over here again to Geogebra. And I want to try plugging in exactly what we just did. So we're trying to look at x squared plus 1. Okay, so this is our original graph. And let's try to do the exact same thing. Without knowing the process, let's just say that I wanted to invert f. Now something really interesting happens here. It's decided to label it as g, it's decided to label it as a function, because I'm trying to create an inverse function, but it didn't get the whole picture we had. Keep in mind, back on the other one, we had both a top and a bottom. I wonder why that is. Why is it that in Geogebra, in the computer software, when I said to invert it, it didn't give me that plus or minus? And the answer is because Geogebra had to make a choice. Do I call it a function, or do I just simply try to flip everything in the picture? And I can't necessarily do both with this problem. So it decided to write it as g of x being a function, but it only looked at the top part. So that's a little bit interesting that we tried to undo this idea of squaring something and adding 1 to it. But we couldn't do that without losing some of that information. So a little bit of interesting, interpretation. This is where the mathematician, where you all lend value that even the calculator doesn't know. It's going to try to give you something that satisfies a function and an inverse, but you know that there is actually half of the situation missing. Okay. So check it against here. What do you see? I'll give you a moment. You can pause the video here to write what you saw in that section. Now, how can we predict this kind of error? That's an interesting question. After all, as mathematicians, we are looking for opportunities for us to find shortcuts in all of our work here. So maybe we look at just where the problem occurred. Let's think. The problem, as I saw it, happened right here. It happened because I asked a question and I got 2 answers in my inverse. Okay. Could I have predicted that before we did the flip? Well, it originally was over here. And so both of those points that I had a problem with is right here. Okay, so if you recall, it's not a function if it doesn't pass something called the vertical line test. So perhaps we can predict that it's about to fail the vertical line test if before we do the inverse, it does not pass a horizontal line test. So we can write down something like not invertible to a function if it fails the vertical line test, or the horizontal line test. Okay, so we've got a little bit of a shortcut now. If something fails a horizontal line test, it might be a function, but when I invert it, we're going to have a trouble with it being a function. If it doesn't pass the vertical line test, then it's not a function whether I'm flipping it, or after like we can't, if it doesn't pass the vertical line test, that's our disqualifier. It has to pass the vertical line test to be a function. It has to pass the horizontal line test to be a function that I can invert. Okay, interesting. So mathematicians say that a function needs to be one-to-one to have a corresponding inverse function with any function that it has. What do we think this means and why? That's interesting. Again, let's see if we can just break down this word, this structure, and see if there's a reason for it. One-to-one. What do we think we're doing when we say one-to-one? One what to one what? Well, functions take one question and give me one answer. That's interesting. Okay, so I can say one question to one answer. But here it says mathematicians say that functions need to be one-to-one to have a corresponding inverse. And we know that inverses mean that I have one answer to one question. In other words, we can go backwards in the storyline. So if we call something one-to-one, really what we're trying to say there is that each question is associated with only one answer, and each answer is associated with only one question. Now we can see that this is a logical way of getting to exactly what we had trouble with when we were doing our graph up here, because that is exactly the trouble we had up here. Up here, every question I asked in my original one worked out just fine. Here was a question, here was the answer. I had a question, it got me an answer. But this one answer, this height answer, was not associated with only one question. It had two questions that got it to that height. So then when I flipped it, that answer became the question, and my questions became the answer that disqualified this from being a function. Okay, so the important thing to notice is that if we ever recognize that we don't have this one-to-one, one question to one answer to one question relationship both ways, then I'm going to have trouble when I try to flip the conversation on its head and still maintain a sense of not being ambiguous or not being kind of confusing. Okay, now, quick history, why is it that this -1 was ever used for describing the inverse function? Because about 300 years ago, there were mathematicians all across Eastern Europe, Western Europe, that were trying to get their ideas across, be the first to publish, discovering beautiful, wonderful things in stride, but there was no common way of writing stuff. So for example, some people would write exponents or functions or oh golly, I'm trying to think, the slopes. They would be writing all of these ideas using different symbols on the paper, depending on the way that they saw math at play. Now, this of course made it very difficult when they were trying to read each other's works, so more recently in history, the world as a whole has kind of gone through a way of trying to standardize our notation, standardize the way that we were describing things. And as it turns out, the one that they chose was this f to the -1 to mean inverse functions. And they chose that because the inventor had used this -1 in an attempt to try to emulate exactly what we do with exponents, where hidden in all of the symbols is do the opposite of exponents, multiplication, one time. Remember what I said, this is the meaning that's hidden in this symbology. You don't just want to take it at face value, you really want to understand the story. So that when we do f to the -1, this isn't to the -1 like an exponent, it's do the opposite of function f one time. kind of interesting. And as it turns out, when you get into later math classes, you will see some things like this. In fact, if you actually have a calculator with you right now, you'll find this button on your calculator. And all this means is, as you might expect, whether you know what sine means or not, is do the opposite of whatever sine is one time. So as I kind of warned you throughout the semester, the best way to prepare for mathematics is to understand the story, it's to understand the model of logic, not to just simply try to do what I refer to affectionately as grab and smash math. You don't just want to see a -1 and immediately assume that that has to be the -1 we've seen before. There's a story happening behind the scenes. It's helpful if we take time to understand what it's saying. Now, as you're going to be working through your problems, it's interesting for us to consider what's a way for being able to check our answers after we get them. Because after all, we've gone through the process of kind of logicking through what I should do going in one direction, but what if somebody just hands me an answer and claims that this is the inverse? What's a way for us to be able to determine if they did it right or not? We could follow them back through all of the steps, or here is my proposal. We could consider that if I have f, which f just takes me from some question to some answer. And then I grabbed that answer and I did f inverse to it. F inverse would take that answer and associate it back to one question. That I should be able to check this by saying, if I do my function and then I do the inverse of the function, it's like doing something and undoing it. So that should allow me to go from x to y with my function f. And then similarly, I should be able to go from y back to x with my inverse function. So it's almost like by doing one function, one series of question-answer combo, I should get someplace else, but if it's a true opposite, I should be able to do the opposite to get me back. So let's play around with this one. We would normally call this composition, by the way, right? The way that we would see this in the previous sections was that it was like I was doing f inverse after I did my f function. So it's like I've got f inverse after f, or sometimes we would write this as f inverse circle f of x. Okay, so these are two different ways of expressing the exact same idea. Actually, these are about 3 or 4 different ways of expressing the exact same idea. But it should make sense that even if I did the inverse one first, that one takes me from y, and I do the inverse function of it to get to some kind of x, and then I do the regular function back again, I should get back to where I started. Okay, even if I started with this one being x and I went off to some kind of y, and then from the y I went back to some kind of x. Again, the idea being that if these are true opposites, I should be able to run forward and run backwards. And again, if this feels weird, relate it back to something that feels more comfortable, like addition and subtraction. How do we know that addition and subtraction undo each other? Because I can always add something and then I can subtract it to come back to where I started. How do I know that multiplication and division are opposites? Because I could do multiplication in one direction, I could do division in the other direction to get me back to where I started. How do I know if functions are opposites? Because I should be able to do one function forward and do another function back to get back to exactly where I started. So let's play around with that, for example. Let's grab some of the ones that we have from earlier. So let's go back up in our notes packet and we'll grab, let's play with one of the other ones. Let's do this x over 2x plus 3 and its opposite. So here I've grabbed the first ones we played with, this x over 2x plus 3, and then I've done the g of x, which is my 3x over 1 minus 2x. And let's assume that I had just been handed these and somebody claimed that they were inverses. In fact, we found them before by doing the opposite, kind of the switching around analysis, but we never really checked that it passed the horizontal line test. We never really checked that we in fact didn't ever have a time where one answer gave me two different questions. So maybe we're going to try this composing idea. This seems like a way that if it works out truthfully, then there should be a time where if I ask any starting place, after I change it and then undo that change, I should get back to that same starting place. So here's the way that I'm going to kind of craft this as a story. I'm going to start off with x. That's the first thing I'm going to do. The first thing I start off with is x. And then we're going to do, again, the function. In this situation, it's talking about doing f after f inverse. So we'll do f inverse first. F inverse is going to, we hope if it's g of x, if it works out truthfully, it's going to take this x and it's going to multiply it by 3, and then it's going to divide it by 1 minus 2x, and that'd be my next place. Then from here, I would want to grab it and I would want to do f to it again. Okay, now the question is what happens when we do all of that? Well, if you do a function to all of this stuff, then it should be as if I am plugging all of that stuff into my function. So I'm going to plug this entire new question, 1 minus 2x, into my function. So this is going to require a little bit of scratch work. Let's do it down here. F of 3x over 1 minus 2x would be equal to taking that entire thing and throwing it into f. So let's kind of trace it through and then I'll highlight it afterwards. So we get 3x over 1 minus 2x is going into the first part where it asks for a question, and then I'm going to divide it by 2 times 3x over 1 minus 2x, and then we're going to add that to 3. Okay, lots going on here. Again, let's take a moment. Let's go back. What is it that we actually did? We said we went somewhere else. That somewhere else was this 3x over 1 minus 2x. That's my somewhere else that I am right now. I'm thinking that this f function is going to bring me back. So if I have my somewhere else and I put it into f here and here, I'm hoping it will bring me back to my original starting place of x. So we're going to simplify this all out and see if it has the exact same meaning as my starting place. Okay, well, how could we write this out a little bit more simply? I have 3x over 1 minus 2x being divided by, let's see, all of this on the denominator. Maybe I want to simplify the denominator first. Let's clean this up. Let's simplify the denominator first. We have 3x over 1 minus 2x still on the top. On the bottom, we're going to have 6x over 1 minus 2x plus 3. That's a lot of stuff still on the bottom. Let's see if we can simplify that out a little bit. So next it would be, let's see if we could do a common denominator on the common denominator on the denominator. Interesting. So that would be 3x over 1 minus 2x. And on the denominator, we would still have our 6x over 1 minus 2x. But I would want to make this 3 into a 1 minus 2x as well. So we could say I will just do 3 times 1 minus 2x over 1 minus 2x. That's my way of getting that common denominator on the bottom. Okay, let's see what we can do from here. That'll get me 3x over 1 minus 2x divided by, and then on the bottom I think we would have 6x's and a 3, and then a minus 6x's, so it would be 6x plus 3 minus 6x all over 1 minus 2x. Okay, we're doing all good. We're just going to keep going. So now I've got 3x over 1 minus 2x, and that's all being divided. I'll do it like this. It's being divided by, how can we simplify what's up in the bottom? 6x and a minus 6x goes away, so that looks like there's just a 3 on the bottom, and then I have a 1 minus 2x on the bottom as well. So that would be right here, 1 minus 2x. Okay, looking good so far. Did I mess something up? I think I might have messed something up. Let's do a quick double check. Okay, no, actually I think that looks pretty good, because notice what I'm looking at here. We can write this entire thing as equals, grab my pen again, equals 3x divided by 1 minus 2x times the reciprocal 1 minus 2x over 3, and then I have things on the top and things on the bottom that are all being multiplied that I can cancel away. So let's use yellow here to show that. I have a 3 that I can cancel away with this 3. I have a 1 minus 2x on the denominator that I can cancel with the 1 minus 2x, and that should leave me back with x. Okay, so we did in fact find an inverse the first time around. Let's go back through and see if we can follow the story. I took x to some place other than x, and when I took that other than x and I put it back into f, that brought me back to what we hoped was the beginning place x, which sure enough, after you go through uncluttering everything that is this function in the undoing, it is. So we went from x to something else back to x, so that gives us our proper definition for a function. And in fact, we can see that it's going to work out down here as well, where here for the f inverse after f, we would see if that would be the same thing as doing f after f inverse. Let's try that out a little bit faster. So f inverse after f would mean that I was doing f inverse after I did f of x, and we would hope that this would equal x. So we could play around with that. f inverse after I do f of x would be saying, okay, f of x takes any question x, divides it by 2x plus 3. And then f inverse of doing all of that grabs that and throws it into what we're hoping g of x is. So that would be 3 times x over 2x plus 3. And then divided by 1 minus 2 times x over 2x plus 3. If I feel like I lost you on this one, let's take a moment and do a quick little recap. So again, what are we trying to do here? We're trying to find out whether or not doing this undoing, this going away and coming back is going to get us back to where we started. So we're going to say that's the same thing as saying I'm going to do an opposite after I do the original. And I can replace the original with something that the original is equivalent to. Same idea, different appearance, different perspective. And then I can take that and I can put it in as the question in what I hope is my inverse. And if this all checks out, we should get back to where we started. So let's go ahead and keep going through with this and removing the clutter, simplifying away to see if we do in fact get the exact same thing. On the top, we're going to get 3 groups of this x over 2x plus 3. On the denominator, you're going to have 1 minus 2x over 2x plus 3. Again, on the denominator, you've got a lot of things happening. We could try to make that into just one fraction on the bottom. So we're going to have 3x over 2x plus 3. On the denominator, we can look at this and say I have, what would that be? 2x plus 3 over 2x plus 3 to try to make it that common denominator. And then I would still have the minus 2x over 2x plus 3. The next line of work, we would say on the top, we're going to leave that alone for a moment as we focus on the bottom. And on the bottom, we're going to have 2x plus 3 minus 2x would just give us, I think, 3 divided by 2x plus 3, which we could write as saying I have 3x divided by 2x plus 3 times, or I guess, sorry, divided by 3 2x plus 3. And to make this nice and blatantly obvious, we're going to do 3x divided by 2x plus 3 times 2x plus 3 over 3, which I should be able to cancel away the 3's, cancel away the 2x plus 3's, and that should leave me back with my original question of x. Wonderful. So this idea of saying, if I do in fact have a true opposite, I should be able to run it forwards, in that I'm going away from my x value to a question, and then I'm using the inverse of that question to get me back, or the inverse of that function to get me back to the original question, or I should be able to do it in reverse, where I treat the undoing as the redoing and the redoing as the undoing. Again, we're doing nothing different than what we normally are comfortable with addition and subtraction. Something is taking me away, the other thing is taking me back, and it doesn't matter which way I look at those opposite ideas. It's going to do this kind of reverse idea. Excellent. So I'm going to leave the rest of the packet for you. I've got a bunch of different representations here to cover the exact same ideas that we've played with. So here you've got the same equations we've worked with, the x squared plus 3 and the x divided by 2x plus 3. Keep in mind, this over here is just a polynomial, a quadratic to be specific. This one over here is one of those rational expressions. But the ideas are going to hold true no matter what kind of function we're playing with. If you do a table of values, that would just be putting in some kind of x values and getting out your y values or your f of x values for each of these. And then you can put down here what the inverse equation is, kind of compare what the structure is. Keep in mind, this one here had an inverse equation, but that equation was not a function. And then you can look down here at like what were the inverse tables of values, and you're going to see that you have this conflict with it being a function or not being a function, because there's going to be some places where those x values are going to correspond with more than one y value, and that's going to be your number one indicator. For the graph of the inverse, you can graph it exactly like we did, and then check to see if it passes the horizontal line test as an indicator for if it will later pass the vertical line test after you do that flip from facing upwards to facing sideways. On the last page, what I have for you is a couple other representations of the ideas that we've talked about today. So the first thing is that a lot of times people will look at how you graph the inverse of a function. They will refer to it as flipping it over this diagonal y equals x line. And again, this should make sense, because if this is where all of your questions are the same thing as your answers, then on one side your answers would be bigger than where your questions were, and on the other side you'd have your questions bigger than where your answers were. So like, for example, this a comma b is going to flip so that it comes up somewhere over here to get you your b comma a. And that's in fact going to be true with every single one of these points. This one's going to flip over and this one's going to flip over, and you're going to end up getting something that looks just like that flip, and something we would describe as saying that it is reflected over that y equals x line. For this one here, same idea. So again, you're going to be looking for something that's reflected over that y equals x line, so that would be something that probably is going to look a little something like this one. So it gives you the ability to sketch this out quickly. On the very bottom, we have a couple of theorems that are from the chapter. See if you can practice recognizing within the technical language and those symbologies which of these answers you think are most appropriate. And if you have any questions, you can call me over, or if you feel like you've got it, why don't you go ahead and write a justification over here in your notes so that when you look back at it later, you remember why it is that these different terms organize themselves into these structures, into these theorems, into these truth statements.